let's jump into the last topic of this course, the wave equation. Let's first give a physical introduction to this topic. First of all, what is the major difference between the wave equation and the heat equation? What I really want you to remember is that the difference between the two is in the energy that the system has. In the heat equation, the energy is dispersed. So you start with a certain situation of heat, and heat tends to dissipate away. On the other hand, in the wave equation, we have conservation of energy. So we are in a conservative system. One of the major examples for wave is the idea of a vibrating string. You take a string from 0 to L, and you look at it while you pluck it. So when you pluck it, you put it in a certain initial condition, then you let it go, and you see the string oscillating over time. So your solution is a solution y that is a function of x, where you are in the string, and time. Let's try to retrieve the wave equation from the physical example of a plucked string. As we did for the Laplace equation and for the heat equation before that, we are taking an infinitesimal interval between x and x plus delta x, and we want to find a balance of forces in the y direction, so in the vertical direction with respect to the string. We base ourselves from the fundamental law F equals m times a in this infinitesimal interval. In this infinitesimal interval, considering a tension on the string on the both sides, F is the difference between the tension times y prime computed at one end of the interval minus tension times y prime computed at the other end of the interval. That is the force. The mass is the density of the string times the length of the infinitesimal interval, and a, the acceleration, is the second derivative with respect to time of y. So now, notice a second that I am distinguishing y prime, where I'm taking derivative with respect to x, and y dot when I'm taking derivative with respect to time. If I divide this by dx, what I have is that rho y double dot equals t y second. Or by shifting the constants all on one side, we have a relationship between the second derivative on time and the second derivative in space. And there is a coefficient in between that we call c squared, that is the tension divided by the density. In a plate, in a two-dimensional plate, we're going to go through the same steps. So the result is going to be a second derivative with respect to time of y is equal to c squared times the delta y. So all the sums of all the second derivatives of y. The Maxwell equations in 3 dimensions do work like a wave equation. So the usual format is the one you see on the left. Nabla times h equals a derivative with respect to time of e and a constant, while nabla times e equals a derivative with respect to time of h, where e is the electric field, h is the magnetic field, and they constantly interact in the Maxwell equation setting. That's why we called it the electromagnetic field. In the same time, the curl of h and of e is equal to 0. If we remerge these equations, we retrieve that we can actually split h and e, in which we can write both of them as a wave equation where the second derivative of time of h is equal to c squared delta h, and the same is true for e, where c squared is this constant 1 over square root of epsilon 0 mu 0. That is actually the speed of light.